We're talking energy coupling?
This power and neutron barrier.
Neutron bands?
Barrier. Neutron barrier. Yes. Band, yes. And independent.
You're saying independent?
Independent.
Well, the issue on energy coupling is how does one go from a nuclear process to heat?
Nuclear.
How do you couple a chemical system, chemical energies to it? How do you couple an EV system to an MEV system? Nuclear systems operating at MEV levels. Chemical systems operating like that.
Beg your pardon?
MEV level. And the force.
Both?
Yes. Thank you.
Okay. Other theorists? We have a donation by Preisker.
Who?
Preisker.
P-R-E-E-S-S.
Excuse me, on my model, could you, under the Coulomb barrier thing, could you also put a 0-point field connection? Because there is a modified 0-point field connection. Thank you.
Dr. Bass?
Okay, the Coulomb barrier is by resonant transparency plus 0-point fluctuation line broadening, which is very important because that overcomes the terrible criticism of Magnus Yandel and Rabinowitz.
How do you couple MEV level
Okay,
nuclear reactions
I defer to others, not addressed.
not addressed? Okay. Do you view your theory as dealing with the surface volume effects, or both, or what do you?
Okay, my model is a linear model approximating three-dimensional, so it could be either. Quantitative, I would like to say a couple of words about the quantitative predictions, if I may. First off, the potential that I use is a Madelung Fermi-Thomas potential, which takes into account all of the charges in a lattice. The potential is validated because it predicts the empirical Schwinger ratio to within 0.3%. Furthermore, I have a theoretical proof of Schwinger's conjecture that all of the energy levels of resonant transparency are dependent upon nothing but the fundamental constants of physics and his ratio. Furthermore, I have a prediction of 7 different possibilities of particles and lattices either work or don't work, and in all 7 cases, I submitted this in 1991 before I knew about it, the predictions are dead on. They either are correct that do or do not work. And I believe this is more confirmation of risky predictions than any other theory currently available.
Next,
Risky.
have we got anyone else? Okay.
What's the name? How do you spell?
Sapphire?
Can you spell it, huh?
We're doing 2. This is
Can somebody spell it for me?
Laforgue. LA.
The new model is only a requirement to explain why the quantum passes are
What's this? What's this?
Oh, okay.
I'm sorry, I can't. Would you listen to Dr.?
Okay.
Maintenant, rapport. I said new model is only a refinement to explain the fractal basis are fractal. The idea is that dots are in permanent state of collision. Permanent state of collision in chemical physics, that means solid state. And consequently, the probability of fusion, the probability of collision is infinite, which imbalance, which potential barrier gives a normal probability of fusion.
Wait, so this would be a modified, the way to get around the Coulomb here is through a model of a deuteron that's modified.
So what do we say here? Modified.
The different answer, the first, I don't know, I have a special effect. Effect on the potential barrier, no. No effect on potential barrier.
What I would suggest is that we're not having much success in understanding your theory at the moment. Maybe what we could do is get you to give us a short statement as to how you handle the Coulomb barrier.
Coulomb barrier, no.
Yes, no dealing with the Coulomb barrier.
No effect.
Okay. Do you have a way of transferring energy from the MEV levels of nuclear reactions to a lattice level heat phonon excitation?
No.
No. Okay.
Okay.
Okay. That's taken care of. Okay.
You ask for surface or volume. Volume,
It's a volume description.
not both, volume.
Not both, volume.
Okay.
The both is wrong.
I don't remember.
Are you quantitative? Have you given us an estimate of the magnitude of the effects that you are predicting? Do you give us numbers?
No, not.
No. Okay. We have Dr. Sapovin's contribution.
I couldn't understand this one. Is that deuteron? What is that?
For the deuterons,
Yeah, I can't understand.
how do you go from a nuclear reaction to coupling it to a heat level excitation of the salt, the phonon level?
Deuteron.
Kinetic? Do the deuterons move fast and smash into something?
Is it a collision of deuterons within the lattice? We'll have to settle with that after. Is it a volume effect? Is that both? Anyone else on the list here? Okay. I'm not sure we really have time to do what we had planned to do. Yeah, that's where we're going next. Tom, why don't we give it a try anyway?
Okay.
Can we get a sheet
The hope was to try to assemble something like this for the conference proceedings. Maybe
Just-
to have a summary of what everyone's doing in a uniform fashion.
Yeah, the objective is to get some ideas to where people are working on some kind of common set of language, and I think the difficulty is obvious. Okay, the first column is the theory. The second column is this an explanation of existing observations?
Which observations?
And which observations in particular? And then the third column deals with the ability to design experiments, the sort of thing Peter was talking about at the end of his talk. His proposal to take a silicon object, put it in the furnace, and measure the gammas. The ability to predict.
Okay, for mine, the post-dictions, if you like, are to heat tritium and neutrons. Or those are the primary.
How about ones that predict and then see?
Well, that's, we're not dealing with truth, if you will, at this stage of the game, right?
I know,
We'll see
there
whether-
was-
Both light water
I'm-
and heavy water.
But I mean, no, wait a minute, but there was a very important one. Giuliano and our theories predicted things that were subsequently seen, and they were based upon ways of looking at things in these cities led to things that were subsequently seen. I mean, we had predictions, not post-predictions, but predictions.
Well, Scott, I think the idea here is to try to assemble some predictions such that the experimentals would be able to have a crack at it and try to resolve it for us. That's the.
We're not doing scorekeeping at the moment.
All right.
The best predictions would be those that can falsify theory, according to Karl Popper. Sir Karl Popper's theory of science is that it's not scientific unless it can be falsified.
Right.
Okay. In terms of predicting things, one thing that I'm predicting is a surface phonon laser. If a surface phonon laser could be demonstrated in conjunction with heat or other anomalies, I think that would be very nice. And if the heat was observed and there's absolutely no surface phonon laser to be found whatsoever, I think that would go a long ways towards disproving the energy transfer mechanism. So the neutron hopping would be by looking for gammas offline.
Let's not explain them, let's just write them down.
An isotope shifts in for neutron hopping.
Gammas and isotope shifts.
Okay. Giuliano is not represented at the moment.
What's the last column in one?
Well, I put quantitative or light water. I just put those in because I heard them, and I don't know that you want them.
I think given where we are in terms of time, let's see, Giuliano was next. Then it was Dr. Lee. Do you have a prediction?
Yes.
Just please don't give me a lengthy. Did you predict heat?
Heat after death.
You have heat after death.
That's explanation. Right?
Explanation, right?
And my prediction is three. The first is the grain size. The greater the better, as long as you keep the loading ratio high. The second is the energy gap in the ion band, deuterium ion band structure.
Just the predictions.
Yeah.
The energy gap.
Yeah, energy gap. Energy gap, the grain size, and the helium. That's my prediction.
What was the second one?
Energy gap. The grain size.
What? Grain size.
Yeah, grain size.
Grain size.
Grain size effect.
Big. Bigger the better.
Yeah, under the condition of high loading.
Under highly loaded grains, the larger the better.
And the third one again is?
Is the helium.
All right,
There
helium
must
4.
be helium.
Helium 4.
But many of these would be true for a lot of folks' theories. What could be?
We're not doing that.
Specific.
He's listing what it is that he says he's predicting. Okay, the next.
It's
The
not
Kim.
good for light water.
Ah.
If you are pure light water, it will not work. Yeah. Pure light water.
No light.
No light water.
Mine is light water and heavy water.
Dr. Kim?
Instead of doing this, would you maybe suggest to organize a sample questionnaire to...
Okay, I actually, with that, that's a very good idea for two reasons. One, we're about out of time. And the second is, I think that for purposes of this is catching everyone cold. I mean, I appreciate the problems of responding.
Just give everybody a chance to correct.
So I think you have some sense of what we're trying to do. And so the suggestion, Peter, will you act as a clearinghouse?
Either that or I'll find somebody.
Okay. Peter, what we would appreciate having from you is
Filling out the question.
the filling out of this questionnaire, and I think probably the best way to do it is for those of you who wish to fill out the questionnaire, why don't you leave your name specifically with Peter? We'll prepare a questionnaire and send it to you. Or we'll have it available. Actually, we can have it here before the end of the meeting tomorrow. That's probably the better thing. We'll prepare the questionnaire. If you wish to fill it out before you leave the conference. We'll take it from you before the end of the conference, and we'll put a questionnaire together, have you fill it out, and the intention is to provide this sort of basic roadmap as to where people are working.
We start session number 5 on cathode loading and materials. The pre-lunch part, the first part of the session, we have 3 speakers this morning. There's one small change. The second speaker will be not Dr. Chilani, but one of his colleagues. And I'll announce the title at the time, but we will start the first talk by Dr. Pons.
I'd like to talk about loading today on the title Materials Surface Aspects of Hydrogen Deuterium Loading into Palladium Cathode. And I don't feel so terribly happy to talk about this because I'm talking about loading only, not excess heat for this meeting. But in the last 15 months, we have had great difficulties in getting good loading. So we decided to study further how we can improve loading and investigate further factors to control cathode loading. So my talk will be summarized here, but I'm sure I will run out of time. So I have given up to go in details for each item. But first of all, I would like to remind you of the factors to control cathode loading from 1 to 11. In the past, I mean, for the ICCF-5, I have spoken about number 1, 2, 3, 4, and especially tellurium on palladium and spattered gold film and temperature effect, and also alloying by rhodium. So we know now effect of current density or overvoltage or isotope effect, acid against base. We know about the effect of cations and effect of temperature, and we know now the cathode loading can be greatly improved by allowing rhodium. So I don't go through these old data again here, but I'd like to talk about those items with red circle here, especially about surface modification and also impurities and load-deload cycles. I could show all the data in a random way, but it wouldn't make sense. So to rearrange or to organize my talk, I have made a very question. Cathode loading, is it due to bulk or surface property? This means, I mean, in the region of high loading, probably higher than 0.85. I'm not going to talk about the loading below 0.85. So, but I'm not sure if this is a good question or not to ask if the loading is determined by bulk or surface property. I'm sure it's a combination of both. But I'd like to specify that each row, bulk property and surface property, on the cathode loading through our data obtained in our laboratory. So to specify the roles of surface and the bulk, I have rearranged my data in 3 ways. The first set of data is modifying the surface for a given bulk substrate. So in this case, we do something on the surface by keeping the substrate constant. So for this category, we have Fioria surface modification on palladium, and also we have modified palladium surface by palladium rhodium alloy film, and also we modified the rhodium alloy by deposited palladium surface. And in this way, probably you can know the importance of the surface on the cathode loading. And the second category belongs to modifying the bulk, the change from something to something, but for given the same surface, by which I mean, in this case, palladium film deposited on the substrate. And the third category is modifying the bulk and or surface. I don't know and or, but for this category, I have had 2 sets of data showing the effect of load-deload cycle and also the effect of annealing of cold-worked palladium. So, but before going through all those data, I'd like to just remind you of very basic things like measurement of Dewar PD in situ under in situ conditions. First of all, fuel cell type closed cell, which we developed, and also the measurement of cathode resistance change, which has been heavily employed by the group at SRI. And to remind you, our fuel cell type systems, this is our schematic diagram to show how we can determine the cathode loading under in situ conditions by using fuel cell anode partially immersed in the electrolyte. But I don't have time to explain again this one. So the next, I'd like to remind you that resistance measurement. But to do the resistance measurement, we should know the relation between the cathode loading and resistance. And so we tried to get this curve, which we call calibration curve, by conducting simultaneous measurement of resistivity change and also loading in our cell with fuel cell anode. So we have had this sort of data for hydrogen, hydrogen loading into palladium cathode in 1 molar LiOH. So our data and the data in the reference are more or less coincide each other. So we are happy. But in this region around 0.95 or closer to 1, we have had some discrepancy between our data and the data reported by Baranowski's group. For palladium deuterium system, we have had this one only up to 0.9, but if we draw a curve, then our curve is in agreement with the data reported by Baranowski's group at very high loading ratio. And you might think I am worried about too detailed, but I'd like to remind you also for the region of high loading that this calibration curve obtained by us and that employed by the group at SRI are slightly different, especially in the region above 0.95. So the number one is our curve, and so number two is the curve reported by SRI group at ICCF-1, and number three is the curve report, I think, currently employed by the group at SRI. So please, Mike, correct me if I am wrong. So if we talk about the loading above 0.95, there is always some uncertainty, which could be at most several percent, depending on the absolute magnitude of the cathode loading. So this may be two small problems. So when we have a piece of palladium, and when we do nothing to clean the surface, I mean not etched, we can know the cleanliness of the surface by conducting so-called cyclic voltammetry, which is frequently employed by electrochemists. So of course we do typical cleaning like rinsing by organic solvent and then ultrasonic sonication or something like that. But if we don't do chemical etching, we have this. So this part shows marked contamination by some unknown contaminant, which is always present in the electrolyte. But if we etch for 1 minute, then we have this much clearly defined cyclic voltammograms, which is well known for electrochemists to show the clean surface, more or less. But if we clean the surface, but still we must do something about electrolyte. I'm showing here the effect of purification, which is called pre-electrolysis, known for electrochemists. So to test, to check the cleanness of the solution, we took the cyclic voltammogram of platinum electrode, which is very sensitive to the impurity in the solution. So this is a clean surface for platinum, but if we leave this surface in the electrolyte for overnight, then we have this red curve which shows the surface sites for absorption of hydrogen atoms are totally replaced by some unknown impurities. But if we do cleaning of this 1 molar LiOD by conducting pre-electrolysis for 24 hours, then even if we leave the surface for overnight, we still have a very clear current due to adsorption, desorption of hydrogen. Although this so-called weakly bound hydrogen region is greatly disturbed, but still half of the surface remains still clean. So this means we have always some contaminant on the surface or in the electrolyte. And this contaminant is not always bad because the contaminant modifies the surface, and this may improve the cathode loading. But if we are interested in getting reproducible data, we should really purify the electrolyte. You may be lucky to pick up just right contaminant, but we cannot rely on that sort of luckiness every time. So we are now using this sort of open cell systems to measure the cathode resistance because this system is much more time effective. We can conduct many experiments in shorter time than the fuel cell systems. This is our current system to conduct loading experiment in 6 cells all together. So if we conduct this sort of resistance measurement, we get this sort of resistance change in 1 molar LiOD. The cathode was, in this case, 49 palladium from Johnson Massey, 2 millimeter in diameter and 4 centimeter long. So cell from number 1 to 6, they behave somewhat in different way. Some is loading well, but some is deloading at this stage. And when we increase the current, then the loading becomes very high, but still the behavior of each cell is quite different. But upon increasing the current density further, all the cells become to behave more or less in a similar way. And if we compare those data with the data taken in the fuel cell systems, we have found this square one, the data taken in open cells, and this red one from fuel cell systems. So we were very happy to see this data because the open cell is always doing better than the fuel cell systems. And we wondered why this happened. And then I realized many criticisms from especially the group at SRI by pointing out that fuel cell anode is a source of unknown contaminant. So we went on to analyzing the electrolyte. But first of all, I'd like to show this data to show the analytical result on isotopic purity of electrolyte. So hydrogen deuterium ratio in 1 molar LiOD before pre-electrolysis and after pre-electrolysis, and after electrolysis in open cell, and after electrolysis in fuel cell systems. So it's very clear that in open cell systems, the hydrogen to deuterium ratio becomes very small, much smaller than the original value, because the hydrogen is preferentially eliminated from the system because it is an open system. But for fuel cell system, which is a closed system, the hydrogen content is much larger than open cell system. So the difference between the open cell and the fuel cell systems is not due to this difference of isotopic purity. If it is so, fuel cell system should give a higher loading ratio than the open cell systems. And we also give surface analysis for all the samples. And especially we are interested in knowing platinum against palladium ratio on the surface. And as you can see, for open cell systems, the ratio is very large, like 50, 11.8, 11, 12, and 0.6. While for fuel cell systems, the ratio is small, 0.3 and 0.2. So this is predicted because open cell systems, the platinum anode dissolves and then gets deposited on the surface. And if we do the SIMS analysis to know the depth profile, we have this sort of very clear distribution along the distance from the surface to the bulk in the range of 0.1 micron. So platinum is very much concentrated in the surface region and then goes down very sharply towards the bulk. And also we have conducted lithium analysis, the similar SIMS analysis, which was originally done first by Professor Okamoto and then Professor Ota in Japan. And our data to show the depth profile is very similar to those reported by Professor Okamoto and Professor Ota. So the lithium is very much concentrated on the surface and then goes down very quickly when the distance is something like 4.1 micron. And when I look at this data, I cannot think of by late Professor Akiya Matsuda and his collaborator, Dr. Noteya, who is among this audience, that they pioneered this under potential deposition of alkaline metals on cathode surfaces. But at that time, there was no way to see this sort of depth profile by equipment like SIMS. But I think this is a very clear data to show the under potential deposition of lithium. But the problem is lithium bad? I can say yes. Is platinum bad? I cannot say yes or no. The reason why I can say yes for lithium is supported by our previous data to show the difference between 1 molar lithium hydroxide and 1 molar tetramethyl ammonium hydroxide without any lithium metals. This data shows the hydrogen to palladium ratio, then the system without any lithium is doing better than the system with lithium. So this data, I think, shows that lithium is doing something bad on the surface. Then I'd like to show the data obtained by conducting surface modification by thiourea. Our original idea is to prevent deloading by poisoning this surface by adsorbed thiourea. But to do this experiment, we have a very serious problem, because if we do this sort of experiment in this sort of system with two compartments, in one compartment we have palladium and platinum anode. Then if we put thiourea to this system, the thiourea is oxidized at anode, and then we cannot keep the bulk concentration of thiourea constant. And so we had to modify our cell to overcome this problem by employing cation exchange membrane here between anode compartment and cathode compartment. Then this cation exchange membrane, which is Nafion 115 in this case, is supposed to conduct protons, but it does not allow to permeate thiourea through this membrane. So in this way, we can study the effect of thiourea. If I show you the data in 2.8 molar sulfuric acid, the resistance ratio is something like that. But if we add 1 molar thiourea to this system, we have a very marked influence, like this one. So the resistance goes down from this to this bottom, and this resistivity ratio at nearly 400 milliamperes per square centimeter is almost 1.1. So the resistivity of the palladium goes back to its original value almost. So the thiourea has a very marked influence on this cathode loading. And if we do this in 1 molar deuterated sulfuric acid, we have this to show the pure deuterated sulfuric acid and the system with 1 molar thiourea. So we have a very great influence of thiourea for deuterium system too. But this figure shows some interesting phenomena, because in this region, the cathode loading is something like 0.97, and the resistance becomes very noisy. And I was very curious, and then expanded this range like this. And I knew the resistivity is changing very frequently between 0.93, in terms of loading, 0.93 and 0.97. So I'm not sure if this is a sign of loading, deloading, which was put forward by Dr. Mallove on the first day to show, he was trying to show that it is necessary to have some fluctuation of cathode loading to give rise to excess heat. So I'm very much looking forward to put this system into our flow calorimetry in the coming few months. So to summarize the effect of thiourea, I have this to show the effect of concentration of thiourea between 10 to minus 4 molar and 1 molar, and then for hydrogen and deuterium system. And to my knowledge, this is, I think, the first case to show the systematic change or ability to modify to improve the cathode loading in a systematic way. Although we have to put a lot of thiourea, still, if we can improve the cathode loading, it could be worthwhile to have this cathode to have thiourea. As I expected, I'm running out of time. So one experiment which I would like to show is, again, the surface modification of palladium by putting a thin layer of palladium rhodium alloys. As I reported in the preceding conference, this 10% rhodium palladium alloy shows very large loading, which is something like 0.97 without doing anything. So I was interested in putting a film of this alloy on the palladium to see if the behavior of palladium can be improved or not improved. I mean, to show by keeping the substrate constant and then putting this layer of alloy film. And to do this, we deposited rhodium on the surface first, and then annealed it at 800 degrees C to make the surface region alloy. So this is the result of depth profile analysis by SIMS to show the rhodium content and palladium content from the surface to interior of the palladium electrode. And this is sputtering time, which is 11 nanometer per minute. So this 100 minutes means nearly 1,000 nanometers, which is 0.1 micron. So in this range, we have a layer ranging from 20% to 0% of rhodium palladium alloys. And we found that by adding this film of rhodium alloys in the surface region, the performance of palladium is greatly improved. And again, one more thing I would like to show is the effect of load-deload cycle. I don't know what we are doing here, but we have found it is very interesting. If we load 0.9 in 1 molar LOD at 200 milliamperes, then if we switch off the electricity current and then wait for, we are switching off the electric current here, then wait for some time until we have deloaded palladium, which shows 0.161 of D over PD. Then at this stage, we switched on the electricity current again at 200 milliampere per square centimeter. So we have found that from this 0.90, the loading changed to 0.95. So we have a very large improvement of something like 5%. So we were very much curious about this effect and wondered if it is true or not. Because when we repeat load-deload cycle, the palladium rod wire shrinks or expands according to the loading ratio. So if this sort of size change is happening, we cannot interpret this data in terms of improvement of loading ratio. So we measured the length of this palladium rod for various Yoga PD and found that if we start from this, the original rod, then increase the loading, the length is increasing slightly, but after the beta phase region, the slope becomes sharper, and then if we come back in a reversible way, but when we go into the loading region in the alpha-beta transition region, then the change of the size becomes irreversible. And then finally, if we deload completely, the palladium rod becomes shorter than its original value, which is from here. So, because this is very interesting, we monitor the change in the beta phase region more carefully by repeating loading, deloading 3 times. So between 0.6 for Yoga PD and nearly 9, we went up, down, went up, down, went up, down 3 times. And then we have found that the change is really reversible. So if we keep the deloading up to something like in the region of 0.6, there is no irreversible size change of palladium. So we can confirm that this load-deload cycle surely improves the cathode loading. So the chairman is speaking for me to conclude. So although I have not shown enough data, but if I'm supposed to say something about conclusion, I would say for high and reproducible loading, I think the characterize and control the surface at molecular level is, I think, will be the most important business. Thank you.
Can I have 2 questions, please?
How can I satisfy the high, the content ratio, the differing paradigm after putting the volume? Because I just, we're doing similar kind of the research, and the resistance of the paradigm is not over the 0.7 or 0.75. We have the maximum resistance and come down as increase of the loading ratio. But after putting the area, the maximum, we cannot over the maximum, right? Your data also. The resistance is just only less than the no solution which contain the no area. So I doubt the loading ratio is still stayed 0.65 or 0.7 or something. How can you make sure?
Yeah, it's a very good point. This one shows the point which was pointed out exactly by you. If we put telluride to 1 molar, this is deuterated sulfuric acid, the maximum goes down. But it is this loading step process is not steady state. So along this line, I'm sure there is a concentration gradient from the surface to the bulk of the palladium sample. And in that case, we have found that the apparent resistance becomes lower than the value when hydrogen concentration is uniform. So, but at this steady state region, we are sure that this sort of concentration gradient has disappeared, and then we can rely on the actual resistance value to see the effect of hydrogen.
Just have one last question. Thank you. Sorry, no, please.
Your concentration on the surface makes me wonder if the bulk is not so important after all as the surface. Would you comment? In other words, the alloy or the nature of the solid as opposed to the surface layer. It sounds like you are opting for changing the surface layer and not doing 1,000 different experiments with various alloys or other solids as opposed to dealing with the surface.
Well, what I meant was we can improve the behavior by improving, by modifying the surface. But it is the maximum which we can do is limited by the property, intrinsic property of the bulk substrate. That is what I meant. So I'm not saying forget about bulk properties, like there is no difference between palladium or palladium-loaded Mallove, but I'm saying for a given substrate, the surface is probably the most important property.
Quick question.
Allow me to disagree with you in one little point about harm of lithium. Because when we talk about the loading, we really talk about formation of new phase, a better phase. I mean, we are far from squeezing approach, yes? And maybe palladium, lithium, hydrogen system is another than palladium, hydrogen one, and a boundary of beta phase content in the classification system is another than the palladium, hydrogen system. Yeah?
Actually, I didn't follow your question. So, are you saying that lithium, hydrogen, palladium is has something to do with?
I mean that lower loading ratio with lithium is equal of another boundary content of beta phase in palladium, lithium, hydrogen system, and it is not hard because we mean not about the loading itself, but about the formation of beta phase and about coexistence of phases, alpha and beta phases in dynamics. If lithium shifts the boundary of content of hydrogen in beta phase, it is not. It doesn't mean that it is harmful. Yes.
But we are talking about the bulk phase property. I mean, the surface region where we have lithium is very much limited compared to the interior of the electrode. So the interior of the electrode is purely beta phase, I believe. And but this could be affected by the presence of thin layer of lithium on the palladium electrode.
Thank you very much. Now go on to the second part of the session. The title of the talk is Study of Deuterium Charging Behavior in Palladium and Palladium Alloy Plates, Changing Surface Treatments by Microsecond Pulse Electrolysis, Dr. A.S. Kalon. Yes. The microphone, please.
Okay, let me correct the title of the abstract book because there was a misprinting. We are going to show a systematic study about palladium plate and palladium plate alloys loading pressure. All these plates were provided by IMRA material, and we have a special thanks to IMRA material for some other support. So, this is calorimeter. It's a fluid calorimeter. The palladium plate is inside. It's a palladium plate square. 25 millimeter, and 1 millimeter over that. And it's easy. It's possible to see here the cooler, and we measure the input temperature and the output temperature. Double check. We have a double sensor to check this. It's important to look at the cooling system. We have a water tap to have a constant temperature for the water, and this is the cooler. And we have a periscopic pump to have a constant flow. Constant flow is very important for calculation of output energy. This is the outgoing gas system, and it's very important to take in account well the gas to know how many hydrogen or deuterium molecules of gases are going inside the palladium plate. The system is a closed system. There is a acquisition system control to open the pressure when we arrive to a defined pressure. So we can calculate the absorption just measuring the charge and the gas increasing in the system. Our system is a computer control. Under computer control, we have enough complicated system for power supply limitation. We use not direct current, but pulse current, and I will show later this pulse current system. So why we use pulse electrolysis instead of direct current electrolysis? Motivation are, if we want to have a very high current density, and we want to avoid to have a production of bubbles, and we want to avoid the very high heating of the cathode, we need to have a pulse system, and in this pulse system, the pulse peak current is very high, many amperes. I want to show you. So it's possible also to measure the electrode voltage during the interpulse. So during the interpulse, there is no limitation to the cathode, and we can use this measurement to have an idea of the over voltage of the cathode. The equilibrium conditions are realized in this system. The electric field is very fast, and especially applied to this double layer on the surface. Also, it's possible to tune the pulse and reproduce the procedure. It's not easy, of course, to have a pulse system. However, we have done, and let me show how. Okay, this is a circuit lock scheme. There is a trigger and a fast power passer. This is the electric cell, and there are some circuits to measure the input power, input current, differential potential between outer cathode and the palladium cathode tension during the pulse. And this is just a schematic idea of the system to realize this very high current pulse. This is a cell. And okay, working condition are we use we work at 5 kilohertz rate, repetition rate. The mean current is 16 milliampere. So it's a very low power, mainly speaking. The peak current is something like 15 ampere, and voltage, peak voltage, is something like 50 volts. So the mean power is just 1.1 watt, but the peak power is something like around 7 kilowatts. Okay, let me show blank test using a gold plate. Here we have the absorption rate, so we can measure the absorption of deuterium in the time. Okay, here it's about electric charge, but electric charge is proportional to the time. So 5,000 coulomb, it means in our system around 1 day. Okay, it's possible to see gold has a very, very low absorption. Low gold, it means also the solution and the inside cell stuff. And the deuterium over gold is very, very low, less than 0.05%. The absorption is just at the beginning, and the loading is negligible. So, but anyway, we take in account this quantity in our calculation. So let me show now what's happened if we change gold plate with a palladium plate. This is the absorption rate. Is normalized to the surface and time. And this is the typical shape of absorption, very high at the beginning and going to 0 in the time. After something like three days, all the deuterium is inside. And this is the deuterium over palladium. And this ratio reaches around 1. I show also this other. This is another plate, different plate, and the same in the same exactly the same condition, working parenting condition, and we have more or less the same absorption rate and more or less the same loading. So the experimental error can be something like less than 10%. So we can write here a band. Okay. Now we perform a surface treatment to the palladium plate, exactly the same palladium plate from the same batch. From all these plates are produced by IMRA, and we just operate some surface treatment. In special way, we oxide the surface, and the difference is very sharp. looking at the loading rate. So let me show what's the difference. Completely different the shape. The first day, the absorption rate is quite constant and drop down very, let me say, quickly. The loading ratio is still very high. These are two plates oxiding with the same procedure, and they have this. Okay, the scale is different now, but this is 1 day. Okay, this is 1 day. So you can see the profile is very similar, and also the loading ratio. So it means this procedure can be, we can repeat the procedure how many times we like, and we have the same results. Okay, we were interested to study some palladium alloys, and special way palladium silver, because this kind of alloy is very often used in cold fusion experiments. Silver is at 10%. This is a typical absorption rate, and loading ratio reach 0.8. Let's take in account we have 10% of silver. If we just normalize to palladium, we reach something like 0.9. Okay. So this exactly the same, not the same. Another plate, another palladium silver alloy was oxidized to the surface, and it shows the same dynamics. The loading ratio is more or less the same. It's happened because the silver inside, the 10% is a lot. Now let's see what's happened with cerium. Cerium, it's known cerium is a strong hydrogen inhibitor, absorption inhibitor. This is the normal plate with cerium. This alloy has cerium something like less than 1%. And the loading ratio is very low, 0.5. If we oxidize the cerium, the structural dynamic is not different by the other, respect to the other plates, and loading ratio increase to 0.9. Let me say it's very difficult to reach very high loading ratio using the cerium alloy. Finally, we test a palladium yttrium alloy. Yttrium is a rare earth absorbing deuterium. The same shape, more or less, very high loading ratio, and we oxide the same plate with the same procedure. Dynamic is not so different by other dynamics, quite different, but not so much. The scale is changed. And also the ratio is very high. This kind of alloy has something like a few percent. Let me show just the results of some excess in energy, excess power. We could see with some plates. This is a palladium plate. All these plates I have shown, and all these plates, they reach very high deuterium over palladium ratio, very high, 1 or more than 1. But this is a normal palladium plate, no surface treatment. And these are two different palladium plates with surface oxided in the same way as shown. Okay, let's see. We have a very anomalous effect speaking about the variation of the excess energy. The first day relate to the constant absorption rate dynamics. After that, we go to a constant excess energy, something like 50%. It's very interesting to see this correlation, to see the possibility for this place in correlation with the absorption rate in the beginning of the loading. We normalize all this data to a blank, we use a go to blank, as I was showing. Here I have a report, a part of all tests we have performed for pure palladium with oxide surface, and these alloys with oxide surface also. The only interesting thing thinking about the excess energy we had when we use this palladium oxide, pure palladium oxide. These other alloys, they didn't show very clear excess energy. We have a problem in this kind of test because our calorimeter can range from 1 watt to 1 kilowatt. So to operate in the charging time, we operate something like 1.5 watts. So the excess is something like 0.5 watts. So we are at the limit of our sensitivity. And if we add excess heat with these alloys, I can't say it's not completely sure because we need to increase the sensitivity of our calorimeter. We didn't expect to have this excess heat at the beginning at so low input power.
Do we use the bump, the last one?
Excuse me?
The bump, BUMP.
The bump happening just with these two plates. Okay. The bump, it means from 50 to 75, from 50 to 80%. This is the bump of variation. Okay. Okay, let me go to the conclusion and remarks what we have learned from this test. First, pulse electrolysis with very high peak current is, according to us, a sufficient condition to overload palladium plates. The consequence is plate metallurgy, something like cold working or high hardness. All these conditions are not more a constraint. We had a very strong problem at the beginning of this study because we were looking for a very hard place. Hard place work, but if we are in this mainframe of pulse electrolysis, we don't need to have hard plate. Let me say, when we use palladium plate, very high hardness, and we warm this palladium plate to oxide the surface, this kind of plate is not more cold working. Okay, so cold working maybe can be overcome. Second, palladium alloys are not necessary to have a palladium overloading. We have some alloys, they reduce the overloading, like cerium, but you expect that. Also, if we use, in special way, if we use parts of the process, parts of the process is still working in this case. So my suggestion is to use pure palladium, but in using to load a sort of pulse electrolysis. Finally, palladium treated surface. We just treat the surface using oxidation. Maybe we can have this treatment in a different way. We can use other condition to treat the surface. This is just one. But if we make a treatment of surface, this treatment strongly modify the absorption dynamics we have seen, and the loading parameter can have influenced by this parameter. So this treatment increase the loading. Also, if we have low loading alloys, it involves particular dynamics condition to increase the heat production. We have just two cases now, but we can try to have other systematics. What we can say, what we learn about this, bulk condition to generate excess heat is not a necessary condition. It can happen, but it's not necessary. And surface dynamic can be a very important condition to realize heat production. And I finish last transparency. Conclusion. What were our goals? To realize a technique with pulse electrolysis to check if this technique works. It works. We observe the electrode surface status, and we observe the influence of the surface on these dynamics. Let me say, most of people, they think deuterium over palladium is very important in these dynamics. I can suggest to observe the variation of the absorption of deuterium. I write this something like deuterium absorption variation in the time. Maybe we have to take into account the variation in the time and in the concentration. So the concentration variation in the time and in the space. So something like a gradient. So we have other goals, and it's very important to realize a stationary system where the loading, the absorption rate is very high and maybe constant. And also we have to check better the correlation with these dynamics, loading variation, and excess heat. Finally, let me say, to go on, now we need to have a reference, something like a theoretical model, and we are expecting from theoreticians some support. Thank you.
Already 20 minutes late. Okay, so
let me make sure your past current and voltage measurement. Did you check that by oscilloscope at that point of electrode, not to make a bouncing or just only one current going?
Okay, our pulse system is a pulse, current pulse. We repeat this current pulse 5,000 times in 1 second. Okay, not only one. And this is our system.
I would like to make sure that's a very, very high current and high voltage, and
yes.
Load impedance is very, very high rather than like reading in a only sub-centimeter length of wire can change the waveform. So let me make sure your current is not bouncing back once.
Yes.
Twice.
Current pulse is very peak current is very high. The pulse is very short, less than 1 microsecond. Okay, and the surface is of course changed by this current. we have some data, let me just show.
I think we can stop here.
Maybe you can discuss this in detail.
Unless you're showing the oscilloscope, then you cannot be able to kind of voltage. Thank you.
Thank you very much. I think we will go on to the last speaker for the morning. This is Dr. Bokomoto, please. Okay, but only the same time. Thank you.
Today, I'd like to talk about our approach to obtain higher deuterium loading ratio of palladium cathodes. This shows the background of our experiment. It is said high deuterium loading ratio is necessary to generate excess heat, especially if DOPD is attained more than unity. Excess heat will be observed with 100% reproducibility. We thought the deuterium loading ratio strongly depends on the material properties. So we have begun to investigate the material properties with great interest. This shows the objects of our experiments. The first one is to identify the relationship between the material properties and the loading ratios. The second one is to attain the higher loading ratios. First of all, I'd like to talk about the measurement of loading ratio. This shows the electrochemical cell. This casing is made of Teflon. Palladium cathode with 4 nickel leads is located in this center. Platinum mesh anode is located around this palladium cathode. The electrolysis was carried out in this condition. The deuterium loading ratio was determined by well-known resistance measurement methods. The resistance was monitored in situation with AC million meter. To convert the resistivity to the loading ratio, we use St. Kelvin short curve to SRI group. This shows a relationship between D over PD and R over R0. Before a series of our experiments, we had to decide the electrolysis condition because we thought the current mode might affect the loading. This shows the effect of current density on the loading ratio. X-axis shows the electrolysis time. Left y-axis shows the resistivity change R over R0, and right y-axis shows current density respectively. This scale shows the D over PD that is usable over 0.75. We carried out the electrolysis with two current modes. One is constant current electrolysis of 2000 milliampere per square centimeter, and another is step-up current electrolysis. In the case of constant current electrolysis, that is red point, the resistivity was almost constant after this peak. In the case of setup current electrolysis, that is black point. The resistivity decreased as current was increased. When we compare these procedures, the loading ratio for set-up current electrolysis was higher than that of constant current electrolysis at this current density. Judging from this result, we have selected the step-up current electrolysis for our experiment. In this sequence, we reverse the polarity to deload the deuterium because it has been reported that anodic stripping is effective to obtain the higher loading ratio. When the anodic stripping was applied in our experiment, peculiar deuterium loading was sometimes observed. As the example, this shows a typical result of the anodic stripping. We compare the loading ratio before and after the anodic stripping. Increase of loading was observed at the same current density. But even if we use palladium rod from the same rod, this increase was not always observed. We cannot control the deuterium loading after anodic stripping. We examine the influence of the process on the loading ratios from 2 points of view. One is process to change the bulk properties, and another is process to change the surface properties. To change the surface properties, we pick up these factors. The first one is purity of palladium. The second one is casting condition. The third one is annealing condition. Furthermore, to change the surface properties, we pick up these factors. They are polishing method, etching by aqua regia, and heat treatment in vacuum. Next, to investigate the effect of this process, we have to decide the basic process of palladium electrode. This shows the process. At the first step, low palladium, of which purity is 395 up, was casting in the air using calcium boron to remove oxygen. Next, annealed to remove the stress. Next, carried work cold working. Next, cast into this size and annealed in vacuum at this condition. Finally, polish the surface by diamond slurry for 30 minutes. From now on, I call this palladium as standard palladium. Compared with the standard palladium, the effect of different processes will be discussed. This shows the deuterium loading of the standard palladium. We check the reproducibility of the loading. As a result, the loading was almost same before anodic stripping. The average of maximum loading ratio was 0.90 plus minus 0.01. Now, I'd like to talk about the result. Various palladium materials and its maximum deuterium loading ratio before anodic stripping are summarized in this table. This shows the effect of process to change the bulk properties. This shows the various process and the number of samples. the average of D over PD, and the range of maximum D over PD values. All palladium samples were polished for 30 minutes to have the same surface condition. From this table, you can see these values for several processes. Did not exceed that of standard palladium. For example, it is said that purity of palladium affects the loading ratio, but our results showed the difference of purity did not affect the loading ratios. Next, this shows the effect of process to change the surface properties. These surface treatments were added on the standard palladium rod, except for unpolished samples. In this case, you can see the increase of loading in this treatment. There, etching by aquaresia and heat treatment in vacuum. Next, I'd like to talk about the details. First, I'd like to talk about chemical etching by aquaresia. This shows the effect of etching by aquaresia for 3 minutes. This red point shows the deuterium loading of palladium rods etched by aquaresia, and the black point shows that of standard palladium. In the case of etched sample, at the initial stage of the electrolysis, after the first peak, a rapid decrease and increase of resistivity was observed. This is peculiar to the palladium cathode etched by aquaresia. At all points, the loading ratio of this etched palladium exceeds that of standard palladium. Next, we examine the effect of etching time. The chemical etching by aquaresia was carried out for these times. Even the short-term etching of 20 seconds, we could see the feature of etching, etched palladium. When we etch the surface for 10 minutes, we could obtain higher loading ratio of about 0.95. In other words, etching is chemical oxidation on the surface. Compared with the chemical oxidation by aquaresia, the effect of electrochemical oxidation was examined. This shows the result. Prior to the electrolysis, a palladium rod was processed by anodic oxidation at this condition. This red point shows a deuterium loading of anodic oxidized palladium. This resistance ratio did not go beyond the maximum peak. This means the loading ratio was less than 0.75. We could find electrochemical oxidation give a negative effect on the loading ratio. Next, I'd like to talk about the heat treatment in vacuum. This shows the loading behaviors of palladium heated in vacuum at 100 centigrades for 24 hours, but the surface polishing was not provided. At the beginning of the electrolysis, temperature change of resistivity was gentle. This means deuterium absorption ratio is very slow. The first peak of R over R0 was lower than that of standard palladium, but the loading ratio attained about 0.94. To confirm this phenomena came from the surface effect. We polished this surface by diamond slurry like standard palladium. This shows the result. The blue point shows the deuterium loading of polished palladium after the heat treatment in vacuum. This loading behavior is agreed with that of standard palladium. Judging from this result, we think surface condition might affect the loading ratios. In the occasion of heat treatment in vacuum at high temperature, sublimation of palladium was observed. We suppose that sublimation might affect the surface morphology. This shows our conclusions. We are able to find two effective methods to obtain higher loading ratio. One is chemical etching by aquaresia. Another is heat treatment in vacuum at more than 100 centigrades. This method modifies surface morphology and affects the loading ratios. We are able to attain the high deuterium loading ratio of about 0.95 using a technique of etching. You may say this value is less than unity, but we think this value 0.95 is already enough high for cold fusion experiment. So we recommend our palladium to you. Thank you.
Thank you very much, Dr. Osmondo. You finished full 5 minutes ahead of schedule. So we can have a few questions. Mike?
Just a point of clarification first. The bar chart that you presented initially of our requirements for excess heat production, they were maximum values. So loading between 0.95 and 1 is sufficient for 100% reproducibility of excess heat, at least in our hands. I'd like to compliment you on a very, very nice presentation of some careful industry. And I suggest that you actually have 3 effective methods to obtain higher loading. 2 of them you put up there: chemical etching and aquaregia, vacuum heat treatment. The most important variable is an adequate and reproducible method of producing the metal. The etching is useful, the vacuum treatment is useful, but you've got to have good metal to start with, and it seems that the contribution that you have made is to obtain a procedure that can produce a palladium stock which is suitable for loading experiments.
Thank you. Carlos?
In the former talk, Dr. Spallone told us that to oxidize the sample is very recommendable to improve the loading ratio. However, your conclusion is that oxide on the surface, at the surface, palladium surface, is not convenient.
No.
Is correct my point of view, or I am wrong? Perhaps
His curves were a little confusing. The thing went down. Down was good loading.
Perhaps I can clarify that point. Your interpretation is exactly correct. What was proved here and has been proved many, many times in the past, the presence of oxide on the surface of palladium inhibits loading and prevents the attainment of high loading. The results of Celani's group, presented by Spallone, suggest the opposite, but the anomaly is the Italian observation, not this observation.
Yeah, but the Italian use microsecond technique. That's also the I think we can have the last. Alice, did you want to have a question? Did you want to have a question?
Do you have a spectrographic analysis of the impurities?
Okay. Spectrographic analysis of the impurities. Do you have?
I have
elemental analysis.
Spectrographic analysis of the impurities in the material. That was the question.
For example, ICP or AAS.
Is it available?
They have. Maybe you can take it. I think we should give a chance to Chelani to answer the last question.
One is when you use DC electrolysis, one you use passive electrolysis. In passive electrolysis, there is large value of voltage on the materials. So this value is enough large that you can absorb the utility. In DC, for DC electrolysis, the voltage can be not enough to avoid production of oxygen. So the different results are quite different. It's completely different approach. We just compare to the
interesting point concerning the cavitation is since the bubble is collapsing on the surface of the palladium, the adsorbed atoms are very, very closely coupled to the surface from the beginning. That's not always the case in these processes. Okay, that was by way of aside. Back to the electrochemical situation. What I'm going to do is deal with extreme cases. I'm not going to deal with intermediate cases. We can break the electrochemical reaction mechanisms down into the following sets, three sets. When we drive an electrochemical process, we can, in the limit, as an extrapolation, we can assert that one, but not both, of the electrochemical processes, and I'll express this loosely, require a great deal more pushing than the other. The one that requires the least amount of pushing, we will state, is in a state of quasi-equilibrium. This is an extreme case. It may not ever attain in practice, but it's a limit. So, for example, in this case, for example, we will assert that the Volmer step is in a state of quasi-equilibrium, but the Taffel step is not. In other words, most of our overvoltage is going into pushing a reluctant Taffel step forward. In this case, it's a simple matter to show that the chemical potential of adsorbed hydrogen and hence the loading in a metallurgically unimpaired sample is related in a manner such as this to the overvoltage. In other words, if we measure the overvoltage versus the reference electrode, we can infer the chemical potential on the surface and hence the loading. This is a highly desirable situation because it's the only situation that leads to high loading. Why is that? Let's consider the second case. In the second case, we're going to invert the situation. We're going to say that the Taffel step is in a state of quasi-equilibrium. This is now indistinguishable from gas phase loading. Notice the equilibrium between the hydrogen molecule and the adsorbed state. In this case, all of the electrochemical work we're doing is being dissipated as heat on the surface. Not doing us any good with respect to loading, and our surface activity and hence our loading is related to the chemical potential of the hydrogen gas in the electrolyte. So we might expect to achieve at best a loading of 0.7 in this case. The third step is actually even worse. When the hydrosity step reaches a state of quasi-equilibrium, we have a relationship very similar to the first, but without the minus sign. That means that as we increase the overvoltage, in a negative sense, we actually deload the sample. Clearly, in practice, will most likely be somewhere in between these two limits. This lower limit and this higher limit may never actually be attainable in practice, although I suspect the lower limit actually is, but they represent a minimum and a maximum loading for a given overvoltage. So thus, if you tell me I have an overvoltage of 300 or 400 millivolts in my experiment, can you tell me the loading? My answer is no, I cannot. Until I know the distribution of driving forces between the relevant elementary steps, one cannot predict the loading. One can only predict the lower limit and an upper limit. Now, that's sufficiently important that I'd like to summarize that. None of this is in any way new, by the way. The first publications in this area were written back in the 40s, to my knowledge, and quite extensive work done by Bob Chris and Little, for example, back in the 40s and 50s. Let's just summarize the situation. For a given overvoltage or current, steady-state loading limiters depend on the details of the reaction mechanism. Okay. In particular, the partial rates of the elementary steps, as determined by the kinetic rate constants, as determined by the properties of the surface, metallurgically determined, as determined by any additives that we may have added to affect the electrochemical reaction mechanism. Two limiting cases. Case number one, non-rate limiting Balmer step, quasi-equilibrium for the Balmer step. Cathode is not in equilibrium with the environing hydrogen. Therefore, we can achieve high loadings, and they are directly related to the overvoltage. However, what we take with one hand, what we give with one hand, we take away with the other. Since we now have a high chemical potential of hydrogen within the sample, any gas that finds its way into a void is pressurized, because it must too have a high chemical potential. This leads to cracking and blistering at higher chemical potentials. In the electrochemical literature, this is referred to as the fast discharge slow recombination step. And then the opposite, the bad state of affairs, non-rate limiting Tanner step. Everything is the opposite. The cathode is in equilibrium with the hydrogen, high loadings are not possible, we have non-pressurized voids, slow discharge, fast recombination. In practice, we're going to be somewhere in between. These are limited cases. Now you may say, well, this is a fairly hopeless state of affairs, we don't know very much, unless we measure the loading directly. In fact, there are some simple relationships that we can derive to help us understand the situation. If we have our desirable state, our non-rate limiting Balmer step, we can write this relationship for the overvoltage and the chemical potential of the hydrogen in the voids. Remember, the hydrogen in the voids is pressurized because it has a high chemical potential. It is found empirically, and I emphasize empirically, that from fairly modest loadings, but we will somewhat carelessly extrapolate to higher loadings, the pressure of the hydrogen in the voids is related linearly to the loading. This is an empirical result, and I'll come back to it later. For modest pressures, the pressure and the fugacity of any hydrogen in the void are equal, because hydrogen is ideal for all intents and purposes. You add those three equations together, and you obtain this remarkably simple result, that the overvoltage is related linearly to the loading in the event of non-rate limiting Balmer step, or if you like, the loading will vary logarithmically with the current. A remarkably simple result, yet I've never seen it reported in my literature. Are there any data to support such a result? In fact, there are. We have some data ourselves at SRI, but I forgot to bring them with me. It may actually be a blessing, because I can now show the data of another group. This is a Komatsu group in Sapporo, a paper presented at the Nagoya meeting, where he carefully sets out to measure loading versus overvoltage and versus the log of the current, more or less in the range I was talking about, more or less. And you see a fairly nice linear relationship. It doesn't matter whether it's acid or base in first order. And a nice linear relationship versus the log of the current. So we can be fairly sure that in this experiment, Komatsu and his colleagues were towards the upper end of the spectrum. They were towards the non-rate limiting, highly desirable non-rate limiting Balmer step, which is highly desirable. So they can achieve high loadings and they vary linearly with the overvoltage. So it's not entirely a hopeless situation. Now I have to quickly move on to the next subject, which is the non-ideality of the highly loaded palladium hydrogen system. It's essential to understand, if you wish to understand the properties of highly loaded hydrogen palladium, that it's a non-ideal system. The hydrogen that is dissolved in the palladium is aware of the existence of its neighbors. all of them. Okay? We cannot assume an independent particle model to which to understand the effect to any extent. The key result is that thermodynamic state functions, in addition to being functions of temperature and pressure, are functions of composition. So again, questions such as what is the entropy of formation of the beta phase? What is the diffusion coefficient of the beta phase? Is the entropy of the beta phase are meaningless unless you specify the composition, because it will vary the composition. Now, the non-ideality has several consequences. One is a nonlinear variation of activity with composition, which has a profound effect on the diffusion coefficient, causing the diffusion coefficient, in principle, to reach very high values, very high loadings, via the so-called thermodynamic enhancement factor. Since there are some data being reported at this meeting and have been reported recently, but mainly on this subject, I won't discuss it any further. Instead, I'll move on to something which is, I think, a little more interest to people in this room, which is the non-ideal behavior of the partial molar entropy. Now, before I do, let me just write down this simple equation, which is basically a reflection of the thinking that has gone into the modeling of the highly loaded deuterium-palladium system in the last 50 years. In approximately 1940, Carl Hagen suggested that we could decompose the chemical potential of hydrogen into an ideal term, which we know to be inadequate, plus so-called excess quantities, which are an attempt to model the non-ideality of the system. Now, of course, only the properties of the state function itself are important. Any addition, any breakdown into various terms is a somewhat arbitrary situation. Only the chemical potential is important. But this particular model, which says that the chemical potential is a function of an ideal entropy term, plus an excess term related to elastic forces within the solid, and an excess term related to electronic terms within the solid, has dominated the consideration of the beta phase in particular for the last 50 years. So you should be aware of it, because it underpins most of the literature that exists in this area. Now, got here some data from Flanagan and Baranowski on the log of the pressure above a given sample, above a sample of either deuterium or hydrogen at a certain loading. We've got some points for hydrogen here at very high loadings in addition. Here's this linear relationship that I was talking about before between the log of the pressure and the loading up to about 0.8, 0.85. There are numerous confirmations of this result, by the way, going back to about 1964. What is immediately obvious is that there's somewhat of a paucity of data concerning both hydrogen and deuterium once we get to loadings above about 0.8. Now, this is particularly important because of the existence, I think now confirmed, both by the work of Stella and Fukai, of some early Russian work, which reported the existence of a PDH1.33, which of course is off scale on my plot, but it's out there somewhere. And it would be nice to have some thermodynamic data concerning it. Well, actually, we don't have very much thermodynamic data concerning even the beta phase by itself. It's interesting that experimental studies become difficult when the pressures reach something on the order of 50 atmospheres, up to 100 atmospheres, which is, as we've seen this week, and we've been told before, it's precisely when this system begins to get interesting. It starts to get interesting at loadings around 0.8 from excess heat production, possibly from tritium production, and as I'll show you later, from the partial molar entropy point of view. And this is when the data run out. Interesting point. Now, as I said, based on the non-ideality of the highly loaded compositions, one can infer several things. I'm going to concentrate on analysis of the relative partial molar entropy, which has been mentioned already by Martin Fleischmann on Monday and Peter Hagelstein today as being important. What is the relative partial molar entropy? It's a term that people bandy around a lot. I'm not sure that everyone quite understands what it is. It is the entropy change for this process. Take half a mole of hydrogen gas at a temperature T and some standard pressure P0, which we'll say 1 atmosphere. And we incorporate that hydrogen into the palladium at necessarily, should the hydrogen find its way to a void, an elevated pressure P because of the elevated chemical potential, the same temperature T and some loading X. This is the relative partial molar enthalpy. Now, we can decompose thermodynamically the relative partial molar enthalpy into a number of terms. This is the Stanley Gibbs-Helmholtz equation which you find in the textbooks. It's more convenient, it turns out, to use this decomposition because we don't have partial differentials with two independent parameters constant as we do here. Instead, we just have one. It makes it easier to measure experimentally. Or we can go ahead and determine this calorimetrically using differential calorimetry as it's being done. Now, before I show you some experimental data, I'd like to return to this breakdown of the non-ideal property into an elastic and an electronic term that I showed you before for the chemical potential. Because of this result here that I'm not going to discuss in detail, the decomposition into elastic and electronic terms works for the partial molar enthalpy just as well as it worked for the chemical potential. If we incorporate this empirical result, I'm stressing it's empirical, that the volume of the sample varies linearly with the loading according to a partial molar volume, then we can write that partial molar enthalpy as a function of composition is equal to that value at infinite dilution, plus a term that the literature calls the elastic term, that reflects the interactions of the hydrogen atom, or ion if you like, with its neighbours in an elastic mechanical sense. So it depends on the partial molar volume and the Bose modulus on the loading. And there's a negative term, and then a positive term is called the electronic term. Normally this is modeled by taking a function that is proportional to 1 over the density of states of the Fermi level. Okay. So what does this function look like? Well, there's an extensive literature on this subject. Here we take, here's our quantity of interest. So, these authors here subtracted off a couple of more or less constant terms to leave them with this quantity here. It doesn't really matter what this is, it's just related to this by some constants. And they plot this quantity versus composition. So here's our elastic term, our favourable mechanical interaction with the lattice, decreasing more or less linearly with the load. Here's our unfavourable electronic term, interpreted conventionally as a relatively penalty-free occupation of the high density of states 4D band in the palladium lattice, followed by a high penalty occupation of the low density of states in the 5S band by the electron that is donated to the lattice from the palladium atom, from the hydrogen atom. So we add these two functions together, we get this function for the partial molar enthalpy. In other words, an initial decrease as the elastic term dominates, followed by a rise to eventually endothermic values as the electronic term dominates. The chemical potential, as Juliana Cabrera showed yesterday, does more or less the same thing, but it's, again, susceptible to the same decompositions. Okay. Now this is very much an idealized view. This is very much an idealized view. Before I go on to show you some experimental data, let me throw out an interesting result. I have no idea. This is the enthalpy of dissolution, the relative partial molar enthalpy at infinite dilution for various elements. Here we have some endothermic values, here we have some exothermic values. What do we notice about palladium? Palladium stands out in this chart because although it's exothermic at infinite dilution, it's almost endothermic. In other words, it's not surprising that eventually the relative partial molar enthalpy should become endothermic. Notice nickel, by the way, which starts out endothermic. I have no idea what the significance of that is, but it emphasizes again, I think, the somewhat unusual properties of the palladium. Infinite dilution, absolutely. I just throw that out to your consideration. Here's an attempt to model the relative partial molar enthalpy, Flanagan and Lynch, 1975. What they're doing here is they're plotting the enthalpy of desorption. Up to now I've been considering absorption, so the signs are reversed. I'm sorry, this is a difficulty that plagues this particular literature, you'll just have to get used to it. No way around it. If you want it plotted the same way that I plotted my earlier curves, it's going to look like that. Unfortunately, what do we we see? Well, we see the result that we might, again, this is a calculation, I should say, which confirms the previous calculation, initially becoming increasingly exothermic if it were adsorption, and then tending towards endothermic absorption. You notice that I've used a powerful analytical method here to extrapolate the data back up to the origin. It's called the dotted line. You'll see that again later. Now, you say, well, that's all very well, lots of calculations, let's see some real experimental data. Here are some real experimental data. Again, plotted all as positive numbers because the authors here, these are experimentally determined, calorimetrically determined, are plotting both absorption and desorption on the same plot, so they've ignored the sign. So again, if you want to put in the units that I put in, it's going to look like that. Okay. Basically, we see the tendency towards endothermic absorption as we go to high loadings. Again, we're going to meet an intercept of about 0.85 as we saw from the theoretical calculations. You're probably wondering what this is. Despite all the fine theorizing that we've done on the nature of the partial molar enthalpy, the phase diagram steps in when we have the alpha beta two-phase plateau. The phase rule demands that the partial molar enthalpy be independent of composition. Up to now, everything I've shown you has ignored that point. But these are real data, so for the two-phase plateau, the partial molar enthalpy is independent of composition. Okay, do we know anything of everything I've shown you so far has been for hydrogen? Do we know anything about deuterium? Here's some more data. These are the calorimetric data for hydrogen at relatively low loadings, and for deuterium at relatively low loadings. Up here we have a couple of data points reported in the literature by Baranowski for hydrogen at very high loadings. You notice high endothermic values. I've drawn used my powerful analytical tool again to draw a dotted line. Exactly like that. The reason I'm using a dotted line, not a solid line, suggesting that I have incomplete understanding of the situation, is that I prefer to try and check these calculations and measurements, and I'm unable to find enough raw data from the Baranowski literature to confirm these points. The raw data that I have found suggests that these numbers might be in error. For the moment, I'm going to ignore that and just draw in this functionality here. You notice that the deuterium points across the axis at a somewhat lower loading. That's not actually as promising as it sounds, but since for a given loading, the partial pressure of deuterium above a sample of deuteride is much higher than it is for hydrogen. So we have to work just as hard to load the deuterium to this point as we do to load the hydrogen to that point. Now, okay, you're saying, well, this is all very nice, this is some physical chemistry, we can probably report this up in a textbook if you want to. What's the significance of all this? Well, we've heard Martin Fleischmann describe what he thinks the significance is. We've heard Peter Hagelstein describe what he thinks the significance is. Independently of their usage, as it were, of this construct, it's important to understand that any enthalpy change, real enthalpy change, is the area under the partial molar enthalpy change. So in other words, if we want to calculate the enthalpy of a transition, for example, let's say we have the sample loaded to 0.9 and we wish to deload it to 0.85, the actual enthalpy change would be this area here. It tends to be not a very large number. In fact, these enthalpy changes are typically rather small numbers. It's the first point to understand. The second point to understand is that everything I've shown you so far is being at constant temperature. In other words, the fact that the sample is changing its composition, the fact that there are enthalpy changes in this analysis does not result in a change in temperature of the sample. We delete the enthalpy at constant temperature. Okay. It may well be that in doing that, by whatever mechanism we can supply the enthalpy, we do change the temperature of the sample. The question is, will the loading change as a result of this change in temperature? And I'll get to that point in a moment as my last slide. Another thing that causes confusion is that since we're dealing with an open system here, since we do not have a constant pressure, this quantity, this integral enthalpy change, is not uniquely defined as heat. That's a very important point. It's only uniquely defined as heat for a closed system of constant pressure. Peter Hazelstein might be concerned more with the total energy change, ignoring kinetic and gravitational effects, which is given by the thermodynamic language. And the internal energy change, that's more or less indistinguishable from the enthalpy change. Now, an important question that arises is, should a change in composition occur such that we are able, using the enthalpy released, we can change the temperature of the sample. Can we, in fact, change the loading? Well, the answer is maybe, not certain. Okay. In the case that we're dealing with electrochemical loading, the rate of change of loading with temperature at constant external pressure is given by a function of this kind. Okay? Just because a process is endothermic, according to the Chatelier's principle, for a closed system means that an increase in temperature will move an equilibrium in a certain direction. We're dealing with an open system. Okay? And this does not guarantee, since the enthalpy change itself is not the driving force for change, instead chemical potential changes are the driving force for change. This does not mean that an endothermic process in an open system will be encouraged, will be moved forward by an increase in temperature. Instead, we have to consider the temperature coefficients of the overvoltage. We have to consider the temperature coefficient of this term, which I haven't had a chance to discuss in great detail, which is the extent to which the Volmer step is not non-rate limiting. But similarly, for the rate of change of loading with pressure, it is not guaranteed that an increase in pressure on the sample will cause an increase in loading. It depends on a number of terms, which we cannot, from thermodynamic principles alone, predict. So, if you do an experiment where, at a given loading, when you raise the temperature, the loading increases, then you may say that these terms have acquired certain values, and this is a testament to the quality of your electrochemical procedures. But it's not guaranteed to happen. Just like one last point to finish, Tom, if you don't mind. The inverse of this argument is important. It is sometimes thought that if we raise the temperature on a sample of a given loading, we must necessarily increase that loading. That is not the case. To show that more often than not, the loading will go down. Is there anything mysterious about this? No, not at all. It just means that these terms here have unfavorable values. That's all. Okay. So, in conclusion, I'd like to say that key conclusion, I think, is that for a sample that is being loaded electrochemically, there are several terms that have to be considered when we consider the changes in the state functions of the various parameters involved. And secondly, we must always bear in mind that the hydrogen atom, when dissolved in the palladium, is completely aware of its environment. It's a non-ideal system. It interacts with all other particles in the system. And with that, on the next slide.
Time for one question, perhaps? Yes, we're here.
Speak up. Well, first couple of slides, you talked about H atoms, H ions, H3.
Yes.
But no mention is made of covalently bonded H in the lattice. And I wonder if that's real. Certainly with certain elements like titanium or aluminum, we play a big part.
Yeah. It's important to understand that in any thermodynamic analysis, the nature of the bonding is irrelevant. All we're interested in are the thermodynamic state functions